Today we'll be working on the following problem. There are two parts. Part A is let a sequence f sub n be a pointwise equicontinuous set of functions on the metric space xd with metric d, and f sub n converges to f pointwise on x as n goes to infinity. Prove that f must be continuous on x. And part B is kind of the converse, f sub n, the sequence be a sequence of continuous functions on a metric space xd. F is a continuous function on x, and we know that f sub n converges to f pointwise on x as n goes to infinity. Now we ask the question, is this set f sub n necessarily pointwise equicontinuous on xd? So pause the video if you want to work on this problem by yourself. Okay, let's see for part A, we want to prove this. So just to recall the definition of equicontinuous set for functions, right? So basically, because f sub n is a pointwise equicontinuous on metric space xd, right? So basically what it means, for any epsilon greater than 0, we can find some delta greater than 0 such that this x f sub n of y, because they are real functions, right? So the absolute value of this is less than epsilon for all x y, satisfying the matrix of x y is less than delta. That's what we mean by pointwise equicontinuous, right? So now we want to prove now f sub n goes to f, right? So for we can pick a fixed basically pick x sub 0 in x. We want to show that f is continuous at x sub 0, right? That's what we want to show. Now if we look at this, so basically we know that for any epsilon greater than 0, there exists delta greater than 0 such that f sub n of x sub 0 minus f sub n of y less than epsilon for all y with d of x sub 0 y less than delta, right? So basically we apply this with x fixed to be x sub 0. So let's read this. For all epsilon greater than 0, there is a delta greater than 0 such that this the absolute value of this distance, absolute value of this is less than epsilon. For all y with, if y is in the open ball of x centered x sub 0 and then with less than delta, because we have for all n, for this, for all n, for all n, that's all n for this, right? For equicontinuous, so that has to be for all x, y, and for all n. And then this one is also for all n. So if for On, let's, we can let n goes to infinity. So because f sub n f sub n converges to f pointwise, right? So this one goes to f of x sub 0, and then this f sub n y goes to f of y, and then less than or equal to epsilon. So what do we have? For any epsilon greater than 0, there exists delta greater than 0, such that for all y in the open ball with a center and x0 radius delta, then f of x sub 0 minus f of y, the absolute value is less than epsilon, right? This means what? It means, which means f is continuous at f sub 0, right? Since x sub 0 is arbitrary, so f is continuous on x. So now for part B, basically it's like a converse of this, right? So we want to prove that, the answer, first of all, answer is no. So now we want to construct a sequence of continuous functions such that is not equicontinuous, but it converges to a continuous function pointwise, right? So we can pick like this x to be the closed interval with Euclidean matrix closed interval from 0 to 1, and f sub n of x is defined to be nx divided by 1 plus n squared x squared, and n from 1 to infinity, and x in this interval, right? Closed unit interval. So let's verify. Then it is clearly, f sub n of x continuous, and f sub n of x goes to 0 for any x. So this we define this 0 function, right? So of course 0 function is continuous. So f sub n of x goes to a continuous function as n goes to infinity, right? So now, but if you look at the particular value, f sub n of 1 over n minus f sub n of 0, if you look at this, f sub n of 0 is 0, right? So this is f sub n of 1 over n, which is what? If you plug in, it becomes 1 over 1 plus 1, which is 1/2. The distance of 1/2, right? It's not going, so basically I have a fixed one distance. So no matter what your delta is, n 1 over n is like, this cannot be arbitrarily small, right? So the family of this is not pointwise equicontinuous. Yeah, that's the counterexample. That's the answer for B. That's it.